Hi, and welcome. In this Daylight Visualizer tutorial, you will learn how to perform climate-based daylight modeling in a building model imported from Autodesk Revit. After starting the application, we need to click on Import Model, select the file to import. In this case, it's an OBJ file exported from Revit, and then click Open. First, let me introduce you to the user interface and give you a few useful tips. The main interface consists of a progress bar at the top, which facilitates navigation through the different steps needed to prepare your daylight analysis and visualizations. The three main viewports show a plan view on the left, a 3D view of the model on the top right, and a section view on the bottom right. Use the blue lines in the plan and section viewports to adjust the position of those views in the model. The 3D view allows you to inspect the model with rotation and zoom from the center of the model. The small icons located at the top left corner of each viewport are tools to help the user perform actions such as taking measurements to ensure the scale of the model is correct, as well as zooming and panning. At the bottom of the interface on the left, you will find options and parameters for each of the steps in the progress bar, and on the right, simple instructions for each steps. It is useful to know that you can zoom in and out with a mouse wheel and use both mouse buttons to pan the model in the plan and section views. It is also very useful to know that you can update the 3D model in an existing Daylight Visualizer project with the Update Project function located under the File menu. Now that you are familiar with the user interface, let's move on. Under the first step, we need to make sure that the scale of the imported model is correct. To do that, we will use the measure icon in the plan viewport and measure the model. In this case, the model scale is correct, but I will still show how to change the scale of the model in case you eventually need to do so. First, I will increase the scale by a factor of 1000, and then I click on the Fit button in the plan viewport to recenter the model. I can now measure that the model is 8 kilometers wide instead of 8 meters, which would create huge issues in terms of simulation time. I will now scale back the model to its correct scale by applying a scale factor of 0.001, click the Fit button again, and perform one last measurement to ensure the scale is correct before moving forward. You can also select the type of units you wish to use to perform measurements under this drop-down menu. Now let's move on to the next step in the progress bar. The second step, Surfaces, is where we will define the surface reflectance values of materials in your imported model. For this step, you need to focus on the menu at the bottom of the interface. On the very left, you will find a list of elements corresponding to the materials present in your imported model. Whenever possible, it is good practice to simplify the model for the purpose of a daylight analysis and to clearly know which parts of the geometry correspond to each element. This is in order to ensure that surfaces have realistic reflectance values, which will also allow you to follow specific recommendations or requirements from rating systems or building regulations in your analysis. Next to the list of elements in your model, you will find a list of the material types supported by Daylight Visualizer. In most cases, the plastic material is what you should use for everything which is not glass or metal in your model. Once you select it, you can quickly assign a reflectance value by choosing from the predefined list on the right, or click on User Defined to input custom properties. Now let's go through the list of elements included in this model. The first element on the list, exterior ground marked with an asterisk, corresponds to the virtual ground plane of the lighting environment in Daylight Visualizer. It is not a part of the imported model and will always be present in this list. A reflectance value of 20% is usually recommended for the exterior ground and is the default value for this element. The next element on the list is DVIS wall. This material name was defined in Revit and corresponds to the interior wall surfaces in the model. Recommended reflectance values for interior walls are in the range of 0.5 to 0.8, but it's recommended to use a value of 0.5 when verified calculations are carried out. To do so, we need to select the plastic material type and then choose a value of 50% reflectance. The next element on the list is DVIS floor. Recommended reflectance values for floors are in the range of 0.2 to 0.4. Like walls, a lower value of 0.2 is recommended for verified calculations, so we will set it to 20% reflectance. Next on the list is DVIS ceiling. Recommended reflectance values for ceilings are in the range of 0.7 to 0.9. We will set it to 70% reflectance. Next element on the list is DVIS timber window frame, which we will set to 50%. The next 6 elements on the list start with a small W underscore. This is a trick to automatically assign those materials as zones for precise daylight measurements in each room. The material properties of elements tagged as a zone are not important since this geometry is only used to represent virtual work planes and does not interfere with the daylight distribution in the room. You should never, for example, tag the floor as a zone. We will select each one down the list and verify they are all tagged as zone. Next element is DVIS roof wind glass. For glass materials, it's important to know how many layers of polygon the window glass has been modelled with. In this case, we have 2 layers of polygon, and we therefore need to use the glass solid material, which assumes 2 layers of polygon. The glass surface material, on the other hand, assumes only 1 layer of polygon. Once you select the correct glass material for your model, you can choose a transmittance value from the list of predefined values or input a custom value by clicking on User Defined. The roof window glass in this project has a transmittance value of 62%, so we select this from the list. Next element is DVIS exterior house. Recommended reflectance values for exterior walls are in the range of 0.2 to 0.4, so we will use a value of 20% reflectance. Next is DVIS exterior ENV for the ground and obstruction around the building, where we will also use a value of 20% reflectance. For the next element on the list, DVIS facade wind glass, it's also important to know how many layers of polygon were used to model the window glass. Just like the roof windows in this model, facade windows panes have been modelled with 2 layers of polygon, and we should therefore use the solid glass material, which we need to set to a transmittance value of 64%. In order to do so, this time we need to click on User Defined and enter a value of 0.64 as RGB transmittance values, and then click OK. The last element on the list is DVIS interior glass, for which we will also use the solid glass material and set the transmittance to 90%. We are now ready to move on to the next step in the progress bar, the location and weather tab. Here we need to set the correct orientation for the building, which is especially relevant when performing climate-based daylight analysis. For this exercise, we will use an offset value of 45 degrees. Next, we will import our weather data file by clicking Import EPW and select a weather file stored on your computer in EPW format. In this case, we will use a weather file for the city of Copenhagen. Once the file is loaded, you can see that the location settings are automatically updated based on the information in the weather file. We are now ready to go to the next step in the progress bar, camera. Here we have a choice of different view types, but for our climate-based analysis, we need to use the plan view. The next thing we need to do is set the height of the plan view in the model space. We can use the section viewport to verify the height of the floor and ground level, and set the view height 850 mm above to measure daylight at a typical work plane height. Now that the plan view height is set, the last step is to set the area for the measurements, which in this case is the boundary of the house. By clicking on Set Area, we get 4 black dots at the extent of the imported geometry, which can be moved to the area of interest for the analysis. We have now set a plan view to measure daylight on the ground floor level and ready to go to the last step in the progress bar, Render. Here we need to select Annual Simulation in order to perform a climate-based simulation. We are presented with a range of settings for our analysis. Resolution is used to specify the size of images in pixels. This setting doesn't have a huge impact on rendering time with plan views and zones, but can have a significant impact with perspective and cross-sections views. The next setting is Render Quality, which can have a large impact on rendering time. This setting should be set based on the complexity of the building model you are evaluating, and a value between 25 and 50% is recommended for verified calculations. The next setting also has an impact on simulation time since it determines the number of measurement points to be used in the analysis. Here we specify the distance between each measurement points both for the plan view we have defined in the previous step, and the precise calculation zones that were part of the imported model and tagged as zones previously under the surface step. Finally, we can select whether we want to render the plan view and/or zones in the model. For the purpose of this tutorial, we will of course simulate both, but note that simulating only zones can be a good way to save rendering time. When we press Simulate, a progress bar will appear to inform on the simulation progress. The amount of time it takes to complete the simulation depends on the parameters we have just defined and the speed of your computer. Daylight Visualizer uses most of the CPU resources available on your computer when performing simulations. If you need to do work in parallel, you can go to the Task Manager and under the Details tab, find the Visualizer executable. Right-click on it and then click on Set Affinity. Here you can free 1 or 2 CPU cores. It can take a few hours for an annual simulation to complete when using a small value for sensor point spacing and a render quality of 50%. When the simulation is complete, a new window will open. This is the output viewer, where we can process, analyze, and save the results. On the top left corner, we can switch between the camera and zones output. On the top right corner, we have options to save the results. On the bottom, we have options to process the results. Annual climate-based simulation results can be evaluated with a range of metrics. Daylight Visualizer supports daylight autonomy, DA, useful daylight illuminance, UDI, and total annual illumination, TAI. For the purpose of this tutorial, I will demonstrate how to process results using daylight autonomy. Daylight autonomy is a metric defining the percentage of occupied hours during a year when a specific point in a building meets a target illuminance level, for example 300 or 500 lux. The first thing we need to do is set the target. The default value is 300 lux. If we change the target to 500 lux, we can see the results will update automatically and show a lower occurrence of those levels across the building. The next parameters let us choose between false color and ISO contour mapping, where we can choose between 4 different color mapping styles. The exposure setting is not relevant when using false color. It will influence the brightness of the illuminance occurrence output when using ISO contour lines, but it does not influence the measured values. The last parameter allows us to set a specific occupancy schedule where only a specific range of hours will be included in the analysis, as opposed to all daylight hours. If I use a range of hours between 9 and 17, the results will adjust themselves, in this case showing a slightly higher occurrence of the desired light level when only considering this range of hours, as opposed to all daylight hours during the year. Now that we've been through all the parameters, let's have a look at what we can do with the camera and zones output, and save the results. In the camera output, we can use the right-click button to read point-specific values. The clear button located in the top right corner is used to clear the values when needed. We can use the left-click button and hold it to drag a rectangular area. If we leave the mouse over this area, a modal will appear showing results. We can also use the left-click button while holding the Shift key to draw a custom area for the analysis. We can save the camera output as an image file by clicking the Save button in the top right corner. The Export button in the top right corner can be used to export the hourly illuminance values obtained at each sensor point to a CSV file, but this is not a function for typical users of the software. Now let's switch to the zones output by clicking on the Zones tab. Here you will find the same parameters for processing the results, but with the addition of a zone selection function. You can inspect the results for each zone by leaving the mouse over and a modal will appear. When you are done processing the results, you can save the zone's output to a report in HTML format by clicking the Save button. It's always best to save the report in a unique folder so that generated files do not get mixed up with other simulations. Once saved, the report should automatically open in your default browser. Here you can further analyze the results and get detailed statistics on the daylight performance of each zone in your model. In order to do so, we will first select the report option for EN 17037. The European standard for daylight in buildings. A short text appears outlining the recommendations for daylight availability, and the results achieved are added below each zone. Looking at the results for the kitchen and living room, we can see that the space achieves 300 lux for 50% of daylight hours, over 92% of the measurement area, and meets the recommended level for daylight availability. It's possible to get even more detailed statistics by enabling the report options for fractions of work plane and percentiles. This can be useful when evaluating requirements from rating systems like DGMB. It's also possible to add some notes at the bottom of the report before saving it as a PDF document using the print function in your browser. You now have the basics to run climate-based daylight simulations and interpret the results with confidence. Use these insights to learn from and support better daylighting decisions in your projects. Feel free to explore more tutorials on our YouTube channel, and thank you for watching.